My name is Tom, and in this video I am going to walk you through a solution to a type of exercise that is common in many statistics courses. So let's begin. You might be asked to find the probability function, or the probability distribution of boys and girls in a family with 3 kids, assuming equal probabilities for boys and girls. Okay, so one more time. What we have to do is, let me switch to the other side to the fine point of the marker here. We have to find the probability distribution of boys and girls in a family with 3 kids. And of course you assume here that a boy is as likely as a girl is as likely as a boy, so the probability of having either one is 50%. Well, let's take a look at what we have. If you're having 3 kids, first let's ask ourselves, what are the possible values of the random variable x? So let's define x. That's the first step in any mathematical problem. Introduce a variable and then give it a clear meaning, so nothing is ambiguous. X is number of boys. Okay? So what are the possible values for this random variable number of boys? Well, let's think about it carefully. You can have 3 girls and no boys, or we can have 2 girls and 1 boy, or 2 boys and 1 girl, or 3 boys and no girls. In other words, as far as the number of boys is concerned, the values of the random variable look like this. Let's draw a little horizontal axis. 0 is a possibility. 1 boy, 2 boy, or 3 boys. These are the possible values of the random variable representing the number of boys a family with 3 kids might have. 0 boys, meaning all 3 girls. 1 boy, 2 girls, 2 boys, 1 girl, and then 3 boys, no girls. So we know that these are the values of the random variable x. Now, what about the probabilities that go with these, right? What's the probability that you will have 0 boys? The probability you will have 1 boy, or 2 boys, or 3 boys. Exactly. Well, this is a binomial distribution for the following reason. Every time you have a kid, the chance of having a boy or a girl is the same. That's the first step. And of course, from one to the next trial, so to speak, so that from the one birth to the next, we have independence. Okay? So in other words, the probability function that goes with this is the binomial one. Okay, you either have a boy or a girl, and the probability is the same per trial, and the total number of trials is known in advance to be 3. Okay, because at most we can have 3 kids here. So those are all the fundamental assumptions of the binomial distribution, right? Independence, fixed number of trials, and a stable probability from experiment or trial to trial. Okay. So find the probability distribution of boys and girls in a family with 3 kids. X is the number of boys. These are the possible values of the random variable x. And now, let's set up the probability function that goes with this. So we write the following. I want to use a different color here for the sake of variety. The probability that x equals some specified k, and k is one of these values, 0, 1, 2, 3, any one of those, is given by k the total number of trials, which is 3. So this is the binomial coefficient you're seeing here. The probability per trial is 50%, so it's a half of raised to the k, times the probability of failure, which of course is now 1/2 to the 3 minus k. Okay, there we are. So let's evaluate this. So the probability that you will have 0 boys is 3 choose 0, like this, 1/2 to the 0, times 1/2 to the 3rd, and all that remains from this, after you simplify these calculations, is 1/8. Okay, there you go. The probability that x will be 1, that you will have 1 boy. That means 3 choose 1. Remember, the coefficient here tells us how many different ways we can get a boy, right? The boy could be the first kid and then 2 girls, or maybe he's the second between 2 girls, or maybe he's the third after the 2 girls. That's why we have to have that present here. That tells us all those possibilities. Then we have a half to the first times a half to the second. Once we simplify this, and I suggest doing this on your calc, this gives a value of 3/8. And then the probability that you will have 2 boys is 3 choose 2, 1/2 squared times a half to the first, which once again is 3/8. And lastly, the probability that you will have 3 boys is 3 choose 3. And then a half cubed times a half to the 0, which once again gives 1/8. So these are the various probabilities. And what might be helpful here now is to actually plot them on like a stem plot, so you can compare them, right? So the highest probability we have is 3/8. So I just count off by 8s here, okay? So our vertical axis will look like this. We'll go by 8, 1/8, 2, 3, 4, 5, 6, 7, 8. 9, that's not important. Okay. So the probability of having 0 boys is 1/8. The probability of having 1 boy is 3/8. The probability of having 2 boys is also 3/8. And the probability of having 3 boys is again 1/8. So it drops off this way, okay? And then this is what we take as the probability distribution. Okay? So one more time. Find the probability distribution of boys and girls in a family with 3 kids. You introduce a variable, give it a clear definition, as I've done here, the number of boys. In this case, you have to make a decision as to the type of distribution. So, to review, the binomial has some essential characteristics, right? And choose k. And then you have p to the k times 1 minus p to the n minus k, right? This is the probability function for the binomial. If you look at this, it pretty much has everything that you might imagine, right? You're multiplying, that means you've got independence. P is a parameter, it's fixed, that means it doesn't vary from experiment to experiment. N, that's given in advance, that is fixed, therefore the number of trials is known in advance. So the rules that you need that govern the binomial distribution are implicit essentially in the mathematical definition of the distribution, which looks like this. And there you go. So that's how you solve this kind of exercise. And this is the probability function. So thank you very much for watching and have an absolutely amazing day.